Yeah, so I participated in the very first one of these heliophysics summer schools way back in the day as a student, just as you all are doing now. Got a ton out of it, helped me a lot. So really glad to see you all here today and that this program's still going strong. So yeah, my name is David Malaspina. I am a assistant professor here at CU Boulder in the Astrophysical Planetary Sciences Department. But I work on spacecraft data, and I primarily work on in-situ data and primarily fields data. So I'll talk through a bunch of that today, what that means, and what that means for what you all are doing. Okay, so I work on in-situ data. What is in-situ data? In-situ data means something that you have measured at the location of the spacecraft. You have measured your local environment. This is very different. When I talk to my colleagues in astrophysics, they all think of photons and gravity waves and neutrinos and things that come from, frankly, somewhere else. Right? But in situ data is the opposite. You're measuring the environment that surrounds you. What does that mean? You're measuring plasmas. So you're measuring ions and electrons. You're measuring electric fields. You're measuring magnetic fields. Not photons, but the ones that are local to the plasma, supported by the local environment. This can also mean neutral gases if you're down in near an ionosphere, or cosmic dust. These are all things that interact with the spacecraft in its local environment. And again, the opposite is remote sensing. So everything else you'll hear about today in terms of data is something that has come from far away, relatively undisturbed, telling you about a distant environment. So that's typically photons in astronomy. That's the main thing. But you also have things like gravity waves or gamma rays or neutrinos, something like that. Okay, so what in the world will we ever want to measure in space? What would you want to measure at the point of the spacecraft? This is interactive. You got to say something. Particle. What particle? Okay. You're saying fluxes. Okay. What else? You say. Okay. What fields? Okay. Of what? Well, more like what would create them? Okay. Maybe the solar wind magnetic field. Where else would you get a magnetic field? Planets. Yeah. We have one right here. We're living in it right now. Okay. How about electric fields? What generates the electric fields? Currents. Okay, that can do it if you have an active current and you're in the middle of the current. Yeah. Waves. Absolutely. Plasmas are full of waves. What else would we want to measure? Composition. There you go. So that's basically what atoms you're measuring or, what ions. What else? You're in space. I threw up some pictures, right? Let's say you're near Mars. What do you care about at Mars? Sorry, say again? Okay. Well, X-rays, where do X-rays come from? So, okay, at Jupiter. What do we want to measure at Jupiter? Lightning. Okay. So yeah, there's plenty you can measure from lightning in situ, right? Not only you don't have to rely on the photons, you can measure the plasma waves that are kicked off by lightning. You can measure ionospheric conductivity if you know the particles that are headed down into the atmosphere. Neutrals, right? So say we're interested in atmospheric loss at Mars. Part of what we need to know is what's the source population? What neutrals do we have to work with that we can ionize and then remove from the system? Yeah. Okay, so here are all things that we would absolutely love to measure at the point of the spacecraft. This is my list. So you kind of want to measure particles. Why do you want to do that? You want to understand basically their energy and their participation in energy transfer. So we can measure protons, electrons, alphas, everything bigger than an alpha I call a heavy. That's something I get from my astronomy colleagues. Dust carries energy and momentum through these systems, and of course neutrals. And neutrals, when you get into composition, you also get into chemistry, right? You don't have to just measure a single neutral, oxygen by itself or something. You start to get molecules. Also, fields, right? We want to measure fields because electromagnetic fields transfer energy from one part of a system to another. When we talk about magnetic fields and electric fields, we typically break them into two pieces. You've got DC coupled and AC coupled. And more or less means something quasi-static and something fluctuating. Quasi-static because, of course, your observation point is moving and the environment is changing, but it can be changing relatively slowly, and that's something you'd call a DC coupled field. Okay, great. Now, why can't I see this? Go away. There we go. So what properties? So now we talked about what we want to measure. What about these things do we want to measure? So let's think about particles. So we got plasmas, neutrals, and dust. What do we want to know? We heard flux earlier, so I'm going to throw that one up here. What else do we want to know about these particles? Energy. Sure. Mass. Yep. Charge. Density. Velocity. Kind of gets in there with energy and mass. It's all mixed together. But yeah. Temperature. Another one that was mentioned earlier was composition. It's kind of like mass, a little bit redundant. Sure. Where were they? Yep. So what about neutrals? Would we want to measure the same things or something different? Sure. So composition becomes way more important for neutrals generally, because if you're seeing neutrals, you're kind of down in the soup of an ionosphere, and there's a lot going on. Energy. Thanks, autocorrect. Okay, what else? Do we want to know where they're coming from? Okay, what if you were measuring dust? Yeah. Yeah. Sure, surface charging. Right. You don't get that with single particles. You just get, ionization charging. But here you can actually charge the whole surface of the object. Nice. What else? Yeah, sure. When you measure an electron, you kind of know how big it is. When you measure dust, it could be many different sizes. Field composition becomes very critical for dust, more so than even some of the other ones. Okay, so there's a couple of good ideas. There's my list. Very similar. For all of these, the most basic thing you want to know is how many of them are there and where are they coming from? Those are generally the things you want to know. The energy, the temperature, the velocity, the composition, the charge state, right? If we're talking about ions, how many times has it been ionized? Maybe you want to know that. There's also pitch angle. So for those of you who have worked in plasmas a lot, you know that pitch angle is sort of the angle of the helix that the particle is making about the magnetic field. If you're measuring something like radiation belts, say at Jupiter or Earth, pitch angle becomes incredibly important in defining the dynamics. Okay, and we hit pretty much everything else. Great. So, fields. What do you want to measure about a field? Let's say magnetic fields. Well, no, fields in general. What do you want to measure? Strength. Great. What else? Direction. Fields are vectors, right? So we need to know the direction. What else? Somebody mentioned waves. How do you define a wave? Say again? Sure. What about those fluctuations would we want to measure? Frequency, wavelength. Well, they can have complicated relationships, and one is much easier to measure than the other. What else? Sure. So strength, amplitude, it's kind of similar, or magnitude, as you like. What about electric fields? Anything different or same stuff? Okay, I'm gonna go with same stuff. There's another thing, of course, you can measure, which is polarization, right? Usually you think about this with photons. You worry about how it's polarized. But plasma waves, of course, also have polarization. And they tell you a lot about what the wave mode is. So this is kind of, are you right-handed? Are you left-handed? Are you linearly polarized? Especially for plasma waves, that tells you a lot. Because a linearly polarized wave is going to end up being electrostatic, right? It won't have a magnetic component, generally. If it's polarized along the background magnetic field. Let me be clear about that. So another thing you might want to measure is the potential of an object. So if you can measure an electric field, you can measure a potential or estimate a potential. Maybe you want to know the surface potential of the moon. Maybe you want to know the surface potential of your spacecraft. These are things you can also measure with electric fields. Okay, great. So we want to measure particle properties. What in the world does it mean to measure a particle property? How do we get a temperature? You don't just measure temperature. That's not a thing. Think about a gas, right? A neutral gas, for example, can be described this way as what's known as a distribution function. Plasmas are also described this way. In a plasma, a distribution function basically says how many particles do we have at a particular location in space, so that gives us 3 dimensions, moving at a particular velocity, that gives us another 3 dimensions, at a particular time, 7 dimensions. So we are trying to measure a 7-dimensional quantity. Ah, crap, that's hard. So what do we do instead? We say, okay, practically what can we do? We can measure things at a particular time, sure, or over some small time interval. And maybe we can measure them at some small location interval, right? So maybe our spacecraft is a couple of meters across, so we say we're measuring in these few meters. And if we build our instruments correctly, we can measure these very narrow velocity ranges. So now, instead of trying to measure all particles at all locations at all times, we've narrowed it down to what's at the spacecraft at this location, x, y, z, moving at velocities, x, y, z, at a particular time, t. So now that we've narrowed all that down, we can sort of measure the local environment. And what you can do is when you're trying to get the total number of particles, you integrate over all of that. So that's the total number of particles you're measuring at a particular time is basically this huge integral. What a mess. And what does that really mean? What does it mean to look at this 7-dimensional space? For a single particle, you usually assume that all these parameters are independent. And if you do that, you're talking about sort of a parcel of gas or a parcel of plasma. And the particles within that can be distributed kind of wherever in this velocity and position space. But even though we can't so much measure every single particle, we can't like take a snapshot of where all those particles are located in time. What we can do is we can measure a distribution function. We can measure how many of these particles contain a particular or possess a particular velocity at a particular location. So within a spatial volume, we can define these kind of bulk properties. This gets back to thermodynamics or sort of basic plasmas or kinetic plasmas. And the bulk properties of a gas or a plasma are the velocity, the density, the temperature. And in this sense, by measuring the distribution function, we don't particularly care about every single particle. We care about the aggregate. How are all the particles behaving together as a gas or fluid? And the bulk properties, these things we want to know, the velocity, density, temperature, they're really derived from moments of the distribution function. And I'll get into details about the moments here. So the 0th moment, this is density. If we take our distribution function and we integrate it over that velocity space, so all 3 velocity dimensions, we end up with a notation that looks like this. We say we'll take our distribution function as a function of velocity only. We integrate over the 3 space of velocities. And the quantity that comes out is the number of particles per volume. Right? So we've not integrated over the spatial volume. We've only integrated over the velocities. So this is our density moment. We can go to higher order moments. So we can take a first moment. Now, instead of just taking an integral of the distribution function with respect to velocity, we stuff another velocity in there. And then normalize against the density. And the thing that comes out is that average or bulk velocity. I'll give you a graphical way to think about this in a moment, but this is the math part. And then if we want to get something like the average kinetic energy, that's our 1/2 mv squared, right? Good old friend. So there's our v squared inside that integral. And we come out with sort of the average kinetic energy. Now, as we're doing this, these moments that we're calculating or from these equations are really only integrating over the velocity space. So still everything is a function of position and time. Right? We haven't integrated out that. Okay, any questions on the math part before I dive into the sort of more graphical way of thinking about it? Wow, you guys are quiet. All right. You can go even further if you like. You can go to a third moment, which gives you a heat flux. You can go to a fourth moment or a kurtosis, and you can see how different from a sort of equilibrium or random distribution that function has become. And you could basically take an nth moment as you feel like by taking sort of v to the n and throwing it in there. And really what you're getting by doing this, by taking moments of the distribution function, is you're getting macroscopic averages of microscopic properties. So instead of tracking every gas molecule in the room, we measure the distribution, we get something like a temperature. That's how we measure fluids too, generally. Okay, so let's do this a little more intuitive. So let's say that you've counted all the particles. We've counted how many electrons and how many ions exist at a particular energy across a bunch of energies. Now we have a distribution function. Here's your most basic distribution function you can possibly measure. So what you're looking at here is the number of particles that you've measured as a function of velocity. The negative velocities are particles moving in one particular direction. The positive are the particles moving in the other direction. This is a one-dimensional distribution function for the moment. So how in the world does this tell me what the density, the flow speed, and the temperature are? Well, these are moments of the distribution. So the first moment, the density, is the integral. So if we measure a distribution function and we simply integrate the whole thing across velocity, we now know how many particles per volume we have. The first moment of a distribution is really just where the peak is, more or less, for a Gaussian. And so that is telling you where the velocity is. So if you see a distribution function shifted away from center, that's telling you the velocity, or the bulk velocity of the population. And then the temperature is the width of the distribution. If you have a big fat distribution, you have a hot plasma. If you have a narrow distribution, it's cold. Electrons and ions will have very different width distributions because their mass, if they're the same temperature, because their mass difference will change the velocities. So roughly, if you have something Gaussian, something like one standard deviation, not exactly, but something close to that, up to square roots of 2, gives you roughly the temperature. Not that you really ever get Gaussian distributions in plasmas unless you're in an ionosphere. So in the solar wind, we treat these bulk moments. Generally, we want to measure density, velocity, temperature. Density is units in the solar wind of cubic centimeters, or 1/cubic centimeter. Velocity is usually in kilometer per second, and temperature is usually in units of EV. Why do we choose those units? Anybody know that one? Why don't we measure it with regular SI stuff? Why are we picking these units? Sure. So as human beings, do you all know what 100,000 is? You picture 100,000 marbles? That's really hard. Human beings are very bad at picturing numbers beyond 100. We can do it with enough practice, we all can, but it's hard. When you want to think about things in a straightforward manner, you keep them from 0 to 100. Those are units that humans are really good at and intuitively connect with. So in this case, what we've done is basically scaled the units. We picked this 1/cubic centimeter, kilometer per second, because if we pick kilometer per second, that puts the solar wind at something like 400. That's a number we can kind of think about. It gets the density at like 10. That's a number we can think about. And the temperature, near Earth, that puts the number at 10. Right? So these are all numbers that are intuitive and easy to work with, and we can do the math really fast. So that's why we've chosen these particular units over something like meters, right? So if I used 1/cubic meters, now I have to put another factor of 10 to the 6 in there, and now we're talking about parts per million, and it gets really weird. So that's why we've chosen these particular units for this particular circumstance. Okay, so we want to measure these things. We want to measure density. That comes from a 0th moment of the distribution function. We want to measure velocity, first moment, temperature, second moment. We also want to measure pitch angle. That doesn't come from the distribution function, that comes from where you're looking in space relative to the background magnetic field. Maybe we also want to measure energy per charge, like if we're trying to do composition or something like that, or if we have multiple charge states. And to do that, we usually rely on charge deposition. So we'll often run the particle through several detectors and see how much charge it deposits as it passes through each one of the detectors. Or there's things you can do with the instrument geometry. We'll talk about that. And then mass, that often comes from knowing the energy per charge, but then also having a time of flight. So if you have velocity and you have energy, you can back out mass, is more or less what we're doing. With neutrals, it's very similar. You still want to measure distribution functions. You still want to know where you're pointed in space. That gives you the instrument look direction. In this case, you're not really worried about pitch angle because it's a neutral, so it travels more or less straight through electromagnetic fields. And so you can get the origin direction just by where you're looking. Energy and mass are very similar. With dust, things get a little more complicated. So to measure, for example, the composition of a dust particle, you have to destroy it generally. So what often ends up happening is they build a telescope, and that telescope accepts a dust particle through the entrance. That dust particle is typically traveling at a ridiculous velocity, greater than 1 kilometer per second, and when it hits your detector, it explodes. And that plasma cloud, it not only explodes and vaporizes, but it ionizes. There's so much energy. And once you've ionized it and you've created a plasma cloud, that plasma then passes through sort of basically a mass spectrometer or something that separates the ions, and you can use that to back out the composition. Fun stuff. Surface charge is way harder. This is usually measured using an image charge kind of measurement, where you have, for example, a grid, a very fine grid, and as the particle passes through, it induces from its surface charge a charge onto those grid lines, and you can back out the surface charge that way, but that's a really hard measurement to make. Okay, so what does it mean to measure an electric field? I'm going to start with electric fields because that's the one I'm familiar with. An electric field, as you all know, is the gradient of a potential, right? So this is maybe the fun thing about electric field instruments is they do not measure electric fields. They measure potentials. That's the only thing we can actually measure. So whenever you see data that says, oh, I'm electric field data, not really. The data is actually voltage data. What we can measure is a change in voltage between locations, and then we have to know something about the separation between those points of voltage, and then we can derive an electric field. Just like with particles, you don't ever measure a density. That's not true. You measure a distribution function and you integrate it. With fields, you don't measure the electric field, you measure the voltage. Okay, on Earth, if you've ever plugged in a voltmeter, if you've ever wired up your house or anything like that, you know that all your electric potentials are measured with respect to ground. On Earth, ground makes a lot of sense. It's the literal ground, right? It's the planet that we're measuring with respect to. What are you measuring with respect to in space? What is ground? That's all you've got is the spacecraft bus, right? There's nothing else there to measure with respect to. So when you're on a spacecraft, your ground or your base potential is the spacecraft. This is problematic. To move the entire charge of the Earth is next to impossible because it's so darn large. But to move the charge of a 1-meter spacecraft, easy. So your ground, the thing you're trying to measure with respect to, is constantly moving. So you're trying to measure with respect to a moving target all the time when you're measuring an electric field, which is sort of the main challenge. So your spacecraft bus is really the ground that you're working with. And what you're basically building when you build an electric field instrument is an enormous voltmeter. All right, so just like the thing you would plug into your outlet to make sure you're not going to electrocute yourself before you take out, rewire your lamp, that is more or less what we're building. It's just enormous and very elaborate. And so when you measure that gradient in the potential, the thing that you're actually measuring is you're measuring the potential on one of the probes with respect to ground, and then you're subtracting off the potential of the other probe with respect to ground. Now, if they both measure ground in the same way, you can kind of subtract it out. But to what degree? That's always the trick. You don't really measure with respect to the same ground exactly. You're pretty close, but not exact. And so that's where the trick comes measuring electric fields. Okay, so you want to measure a voltage in a plasma. Things actually get way more complicated in the sense that your sensor gain is now set by how you're coupled to the plasma. And you couple to the plasma resistively and capacitively. To couple to the plasma resistively, that's the particles that get exchanged between your sensor and the plasma. These could be photoelectrons, these could be thermal electrons, these could be ions. Any particle that passes between the plasma and your spacecraft provides a resistive coupling. At the same time, you have a capacitive coupling. So whatever voltage you drive on your antenna is going to affect the voltage in the plasma by rearranging the particles in the plasma. So you have both a resistive and a capacitive coupling. One of these is driven by the plasma, that's the resistive part. One is driven by the shape of your antenna or sensor, that's the capacitive part. So you'll notice, if you ever go, as we go through spacecraft, that electric field instruments have very specific geometries. And they do because of this. You're trying to keep your gain up. The other issue is that your ground is always changing because any object in a plasma, whatever it is, a dust grain, nanometer dust grain all the way up to a planet or a moon, has the same sort of behavior that it will try to balance the amount of current headed to and from that object. And the idea is to make that current, sort of net current, zero. And so the object will float to whatever potential it needs to ensure that the net current to and from is zero. And all kinds of things can do that. You'll get photoelectrons, you'll get thermal ions, thermal electrons, things called secondaries. So if you get hit with a high energy particle, it kicks off other electrons. And so that causes your ground to float around. The other issue with this is Debye length. So hopefully you all are familiar with Debye length in a plasma. It's basically a shielding distance. It's the distance over which charges in the plasma rearrange themselves to cancel out a net charge that exists in the plasma. This basically creates a sheath around everything you're trying to or using to measure the plasma. And so you have to understand how your signal translates across that sheath, which is another complication. So that's electric fields. Oh yeah, one more bit about electric fields. They're measured in two ways, and you can immediately, by looking at a spacecraft, figure out what they're trying to measure. One is an antenna. With an antenna measurement, the entire sensor is measuring the voltage. So the voltage you're getting out of this is literally the integral of the voltage across that whole big long sensor. This is really good for high frequency stuff. This is terrible for low frequency stuff. It's really good for high frequencies because, remember, at high frequencies you couple to the plasma capacitively. So the image charge on the antenna is influencing the environment and likewise. But resistively, the particles that are created on or near the antenna can now reach the spacecraft. And particles created on the spacecraft can now reach the antenna. This makes your resistive coupling really strong, which makes your DC gain terrible, which means you can't measure low frequency fields under most circumstances. So for low frequency measurements, you have this other double probe technique. This is more like your voltmeter at home, where you have two separate probes and you put them really far apart. In this case, the booms don't measure anything. These are just mechanical structures designed to hold your probes as far as they can from the spacecraft. So it kind of depends what you're trying to measure. Okay, magnetic fields. So what the heck is a magnetic field? Of course, a magnetic field is only an electric field in a moving frame, more or less. How do we measure these? There are two main ways to measure magnetic fields. One is you measure a voltage on a coil, right? So we can go back to Maxwell's equations, and we can say that as long as I have a magnetic field through some area, that's going to induce a voltage on a conductor, any kind of sort of closed conductive surface. So that's one way to do it. You can do Faraday's law. And then there's another trick that folks have figured out over the years, which is to measure it using quantum energy transitions. That's a neat trick. So basically what you do is you excite a bunch of, usually some kind of gas like rubidium. You often use a laser to excite them all into a higher state. And then you the natural magnetic field applied to it kind of gives an energy shift to those levels, and when they decay, they give off photons. You measure those photons. You look for that very fine energy transition, and it tells you the magnetic field. Neat trick. Okay, so we went through a lot of stuff, right? We went through particles, we went through electric fields, magnetic fields, and dust and neutrals. What are we actually measuring when we measure any of this stuff? What is the literal measurement? It's only voltage. At the end of the day, the only thing we ever actually measure is volts, which is a weird thing to think about. And why is that? So that is because the whole apparatus of electronics that humanity has developed really only measures voltage. That's the only thing it does. So how do we get our particle and field measurements into something we can actually understand? This is how. Here's the whole sequence of events. This is spread over many slides, just a heads up. So the first thing is you have some kind of particle or field in the plasma. Great. It encounters your detector. Your detector may be a particle instrument, maybe a fields instrument, whatever. Somehow that particle or field information is translated into a voltage, maybe a current. Once you have that voltage or current, you then force it through an analog circuit that makes it a voltage anyway. So even if you measured a current, you still make it a voltage. Once you have that voltage, now we can start to apply all the tricks that we as humans have figured out related to electronics. So the first thing you do is you force it through what's known as an analog to digital converter. This takes a voltage and makes it into a digital, binary number. Okay, that sounds like it might be the end of things. Not even close. So now that you have this binary number that represents your measurement, you push it through a processor, often an FPGA or field programmable gate array, which is sort of like a very efficient custom processor. And then you packetize it. You jam it into a shape that we know about with something like a header and a tail and an error correction and data hanging out in the middle. And then you stuff it somewhere on your spacecraft in a memory. A memory is just something that holds a bunch of ones and zeros, like a pattern of ones and zeros. Okay, great. Now it's in some storage device that I hope doesn't get hit by a cosmic ray and change the ones to zeros randomly. So now I have it in that storage device. I have to get it to the ground, so I send it through a radio. Now I have to translate it into the radio language. That gets sent to the ground. Now I have a receiver somewhere on the ground, maybe some big 70-meter DSN dish, maybe, I don't know, maybe just a rooftop thing like over at on East Campus, maybe one of the Amazon ground stations that you can now purchase time on. So you can buy your spacecraft communications in the same place you can buy diapers. That's weird to me. Now you've got it on your ground station. Well, now it's in their memory, which has a totally different format and arrangement from the spacecraft memory. Okay, maybe then it goes out to some cloud server, which now has a totally different set of arrangements of data structure. And then you repacketize it. It ends up at your science operations center, where your scientists and engineers and data scientists take it and calibrate it and try to understand what it is we actually measured from that number. After that calibration, it eventually makes it to probably you all, the instrument teams. Instrument teams then iterate on the calibration, goes back and forth between storage a lot, and then it pops out as something useful for science. Wow. Okay. So the point I want to impress upon you all today is an awful lot happens between the measurement and when you actually have something that you can manipulate on your computer. A lot. And at every point in that process, there is an approximation made. Every single step approximates something. Maybe it's in the 15th decimal place, maybe it's not, but it's absolutely approximating somewhere. And there's uncertainty and/or errors can be introduced at literally any stage of that process. So when you look at data, what I'm trying to impart upon you is that maintain a healthy skepticism. Don't believe everything you see in your data. Or try to understand where it's come from. So the short way to say this is trust but verify, right? And I want to bring this up in this group in particular because I know you all are focused on machine learning, and machine learning is kind of like a meta processing of the data, right? So at some point you're trusting that that data is perfect. It's not, right? So as you apply these machine learning algorithms, as you pull out these very subtle patterns in the data, know that those subtle patterns may not be physical, right? So treat them as if they are, but be suspicious that they may not be until you really know, because they could come from anywhere in this big long chain of events. Okay, that's all I wanted. I'm off my soapbox now. So any questions about this part of it? Yeah, sure. Right. So one of the key things to know is what was the method of collection? That's where most of the uncertainty gets introduced, is in that very first detector step back here. So if you know enough about how the limitations of the detector, often that'll give you the answer. It'll let you understand. For example, one of the spacecraft that I work on is Parker Solar Probe. Solar Probe has a very fundamental limitation in that it must hide behind a heat shield. If it's not behind the heat shield, it melts in, I think, 30 seconds at close approach. So if you're behind the heat shield, you fundamentally have a field of view limitation. Your particle instruments can only look in a certain direction. So if you're trying to do something like understand a three-dimensional velocity moment, right, the density or temperature, you can't do that because you can only see in one direction. So you're immediately introducing a bias. So understanding the measurement device and its limitations are the very first thing to look for. The other thing that may be helpful is if you see patterns that are simply too human looking. So a lot of these manipulations that happen to the data happen in base 2, right? Because they're binary operations. So if you start to see things in your data that involve numbers that are base 2, you can almost be sure that it's a problem in the processing and not in nature. So if you see the number 256 come up a lot, or 1024 come up a lot, or changes of that magnitude, now you know something's way wrong. Other things, human signals tend to be at very narrow bandwidth, and they tend to be at fixed frequencies, human chosen frequencies. So if you see a frequency in your data that's at like 50 kilohertz and it stays at 50 kilohertz, very likely human created. Your spacecraft may be creating that signal. Nature doesn't like to pick nice round numbers like humans do. So there's things you can know about the way humans treat information versus the way nature creates information that let you discern, help you at least hint at what might be real and what might not be. Other things you can use are changes that you know happen to the spacecraft. Like say your spacecraft is around Earth and it goes into eclipse and suddenly your data change. Probably it had to do with going into eclipse and may or may not be part of the natural physics. So there's things like that. You can look for thruster firings. You can look for times when commands were sent, when the spacecraft changed orientation, all that kind of stuff. But what this means is that you don't just raw trust data, right? So when you're throwing a machine learning model at something that's great, and that kind of meta processing is important, but you should understand the lower levels of what's happening. Okay, I got to speed up here. So, example, electrostatic analyzer. How do we measure a distribution function? This is a concrete example of how things are done. This is what's known as a top hat electrostatic analyzer. What you've got going on here is you have this outer grid that is held at a potential to sort of remove some species of particles that you don't want in here. So let's say you're measuring ions, you would bias this grid to reject electrons. These are what's known as deflector plates. So you put a potential on there and it allows you to sort of steer your field of view up and down a bit. When a particle enters this aperture, it then passes through this very narrow channel. And you have this kind of dome-like plate, an interior one and an exterior one. And you set a potential between those plates, and that allows particles of only a specific charge to mass to make the journey all the way through this detector and land, or sorry, all the way through this sensor and your detector. When it hits that detector, your anode, there's lots of ways to measure it. Sometimes you just have literally a plate and you're measuring the amount of charge that hits that plate. And so you can interpret that as a current. Sometimes you might have a microchannel plate detector, which is something that creates a cascade of particles. So one particle hits the microchannel plate. This is what's drawn on here. Creates a shower of electrons that bounces and creates a shower of electrons that bounces, and it basically amplifies your signal. This allows you to measure really small things. So you may have a microchannel plate at the bottom of the thing. This is a real electrostatic analyzer. This is a cross-section of the one on Parker Solar Probe. There's a lot going on here. So on the left, you can see that top hat structure. This is the one that measures electrons. This is the one that measures ions on this side. The ion one also has a time of flight assembly, which allows you to measure how long it takes the particle to pass through essentially this space. That gives you the velocity. And since you know the energy and then the velocity, you can back out mass to some degree. And then in here is all the guts. These are the electronics. These are the things that are taking those signals, converting them to voltages, converting them to digital numbers, and then passing them off to the memory. And all told, it kind of looks like that. Another example is a Faraday cup, another way to measure a particle distribution function. So in this case, you have a bunch of grids at the front of this structure. And those grids are essentially designed to filter only particular velocities. So they only allow through a certain velocity at a certain time. And what you do is you change the potentials on the grid and you scan through your distribution function. Remember, we want to know the number of particles at each velocity. So we switch which velocities we can measure and then walk through the distribution function, kind of drawing it out over time. Yeah. So the spacecraft velocity does create a big issue with Solar Probe, in particular because it gets as fast as the plasma, right? The solar wind is moving close to the sun, 200 or 300 kilometers per second, and the spacecraft is moving 200 kilometers per second sideways through it. So you get a windsock effect where the plasma comes in at a funny angle. The way they deal with that on Solar Probe is the Faraday cup looks straight at the sun, and the other one, the electrostatic analyzer, looks off to the side. And so we get coverage of this direction and that direction. So as the windsock effect pushes the solar wind to a different direction, a different sensor picks it up. So oftentimes you'll see this on spacecraft where you have either redundant sensors or multiple sensors that have different techniques for measuring things that cover a measurement. So that's another way you can look at your models and try to understand what's happening is if you run your model data comparison with one data set or with an overlapping data set, you better get the same answer. But if they're measured different ways, right? Like here you're measuring electrostatic analyzer versus Faraday cup, that's a different technique, but they're measuring the same thing. So if you can, get the same answer from two different techniques, that gives you a lot of confidence. There's also, for high energy particles, you use what's known as a telescope. It's generally a stack of silicon wafers, more or less. And so when a high energy particle comes screaming through that, it deposits a bit of energy in each layer. And you can measure that energy deposition. It gives you a little bit about the energy of the particle coming through and a little bit about the direction in which it comes through. Typically, these kind of instruments, it's sort of like looking through a toilet paper tube. You have to point it in many different directions to get a full view of the sky. The problem with these kind of instruments is that the particles that are coming through them are so high energy, they can come from anywhere. They can go screaming through the spacecraft from behind. How do you not count that as an observation? You only want to see what's at the end of your toilet paper tube. You don't want to see the stuff that's coming from the other directions. And so typically these things get shielded to heck and back to keep the particles from the side from counting. There's even fancier particle telescopes. This is another one on Solar Probe. In this case, you get a start signal when you punch through a thin foil. You get a stop signal when you hit a detector, and you can use that to sort of figure out the velocities. And that leads to these weird geometries. This thing, when you look at it, it looks like a big old mushroom. It's a very funny thing. Okay, and electric field instruments, as I said before, there are antennas. So this is an example of antennas. This is the stereo spacecraft. The stereo is basically a camera. That's what it's designed to do. And it incidentally has in-situ observations on it, in my opinion. It was really designed around the camera. And whenever you do that, cameras don't like to move, right? You don't like to be spinning when you're trying to take a picture of something. And so your spacecraft has to stand still. And that means your electric field instrument is limited in what it can do. You can't make it very large. So what they use are these antenna type measurements and go for high frequencies, which you can do well. In this case, they're using rigid structures. On some others, you can spin your spacecraft. So you can imagine your particle instrument has a finite field of view. And if you spin it, now you can take your finite field of view and spread it around the whole sky and therefore get a full picture of the distribution function. So the particles that are coming at you from every direction. Electric fields and magnetic fields also like to spin. So this is a fundamental conflict, I suppose, in spacecraft design. is that spinning spacecraft are really good for in situ, really bad for cameras. Stationary spacecraft are really good for cameras, really bad for in situ. And there's always this trade. But electric and magnetic like to be on spinning spacecraft, typically. Okay, and then my one last thing I got to throw in about electric field instruments, because I do these. Yeah. Oh, yeah. Yeah. Your spacecraft, every spacecraft disturbs its environment, always. We actually use it to understand the measurement. So one of the great things about a spinning spacecraft is that you know what frequency the spacecraft is spinning. And therefore, you know what frequency to expect in your data. And you can use that and you can say, well, at a different phase in the spin period, when I know the probes were oriented a particular way, I see a particular measurement, and that can tell you about how it's impacting the environment around it. So yeah, we take a disadvantage and then use it to make the measurement. Okay, so electric field instruments to scale. So remember, your spacecraft is your ground, which you're measuring with respect to, but you don't want your spacecraft to couple to your probes. How do you decouple things in a plasma? You get the hell away from them, right? So if you're many debye lengths away, the plasma will insulate you from any potential. So if your spacecraft is out of potential and you want to be insulated from it, you got to be something like 5 debye lengths away, roughly. So real quick, how big should these things be? What's the debye length in the solar wind? Let's say near Earth. Oh man, anybody know this one? Anybody know the math? What's the debye length? Uh-oh, pop quiz. Okay, what's the debye length related to? Temperature and density. Okay, there we go. Okay, so less dense plasma gives you a longer debye length. Yes, because you have fewer charges to do the shielding. And a hotter plasma gives you a longer debye length because they can move further and gives you less shielding. So yeah. More than a few meters, not quite 100 meters. So in the solar wind, near Earth, a debye length is 10 meters. That's like stage, right? Pretty big. So if you want to make a measurement in space of electric fields, and you have a 10-meter debye length, and you have to get 5 debye lengths away from your spacecraft, now you're talking a 100-meter structure to measure an electric field. That's huge. So the way they do this usually is electric field instruments are kind of reeled up like fishing line. And they kind of have a weight on the end, and the spacecraft spins, and the force pulls out this long cable and keeps it taut. That's great. It gives you 2 dimensions of electric field. Good luck getting the third. There's no great solution for that, except on MMS. That's the only spacecraft that's ever done that, gotten the 3rd axis of the electric field measurement. But there are some other ideas that exist that may allow you to do this. But what this means is that it's enormous, right? You're talking 100-meter tip-to-tip structures. So if you have a 2-meter spacecraft and a 100-meter tip-to-tip boom, what's a good analogy for that? Again, humans not so great at these kind of numbers, so let's make it more human. What's a 2-meter structure in the middle of a 100-meter structure that you can think of? A windmill. Oh, like the windmill blades. Sure, the center of a windmill to the edge of a windmill blade. Yeah. Anybody got another one? Yes, a person on a track, right? So one person to the scale of the entire track. My favorite one is a hot dog cart in the middle of a football field. That's the size of your spacecraft to the size of your instrument. Wild. Anyway, love that stuff. Okay, magnetic fields. So magnetic fields, this kind of instrument, this is what's known as a fluxgate magnetometer. This was developed long, long ago. 1920s, 1930s were the first versions of this instrument. They've been iterated on ever since. They got a big boost when it was realized they could be used to detect submarines. That's when people really decided to build these things. But what they are is basically a permeable core, right? Something like iron that pulls magnetic field lines into it. And what you do is you apply a current to that core, and you shift the magnetic field, or sorry, a wire wrap around that core, and you shift all the magnetic domains. Anybody know how you make a fridge magnet? Where do those come from? Whoa, okay. We've all used fridge magnets our entire lives. Where in the world do they come from? There's not like a fridge magnet mine or anything. It's just iron, right? You get a chunk of iron, you wrap a coil around it, you force a current through that coil, it creates a magnetic field, it takes all the magnetic domains in that iron and forces them into the same direction. Then you turn off the current and they're all stuck in that direction. Now you got a fridge magnet. This thing works in a very similar way. You apply what's known as the drive winding, so down here, wrap it around that permeable core, you put a current through it, it forces all the domains in one direction. Then you apply a current in the other direction and you force all the domains back the other way. And as you're moving back and forth between flopping the magnetic domains, you trace out this hysteresis curve. And you use that hysteresis curve and, to really understand the magnetic field, because the natural magnetic field is going to set kind of the hysteresis part of that. So you have your driving field, and then you have the natural field that's going to perturb what your driving field is trying to do. So that's more or less how a flux gate magnetometer works. Flux gates are great because they're incredibly robust. It's literally a piece of iron with a wire wrapped around it. That's it. This is great for spaceflight because it's very, very small. You can make them like this big. You can kick them down the stairs and they work fine. They don't care about radiation or vibe or, well, thermal they care about. But they're very tough, robust, cheap instruments. And they give you vector directions, which is excellent. And they're super low mass. They're relatively easy to manufacture, to a point, asterisk there, except for the core material. The core material is super critical. The ability to flip those domains back and forth easily in a way that you can also measure the background magnetic field that's perturbing that flipping is actually quite difficult. That's the magic sauce behind flux gate magnetometers. And the other trick is that they really are sensitive to temperature. You can imagine your magnetic domains, as you heat things up, they expand. As you cool things, they shrink. That's going to change that hysteresis curve. So they are very temperature sensitive. Downside. That's why people worked on the quantum magnetometers instead. Search coils, also super robust, are literally just Faraday's law. You take a ferrite core and you wrap it with a coil. As the natural magnetic field changes, it induces a voltage in that coil. Done. Easy. Except you need a lot of turns. A space-based search coil magnetometer may have up to 20,000 or more turns of very, very fine wire that have to be incredibly precisely arranged in order to get a good measurement out of it. But the other problem with search coils is you're not getting the DC field. You don't get the background. So if you want to measure the planetary magnetic field, if you want to see the solar wind magnetic field, this is not going to help you. It really gets you waves. Okay, so we've been through all these things. Now I'm going to tie it all together with the MMS mission. And the reason I'm going to talk about this mission, because it has 100 in situ instruments. Wow. Remember, every one of these instruments behaves differently, requires a special calibration, a special data pipeline, its own memory and everything. And they're all measuring different things at the same time with 100 instruments. What a mess. Here they all are arranged out on the deck. Oh my gosh. Why are we doing this? Why do we go to all this expense? We're doing this because it's trying to measure magnetic reconnection, in particular the electron diffusion region where all the kinetic physics takes place. So MMS is capable of measuring a full three-dimensional electron distribution function every 10 milliseconds. That's incredible. Before this, the state of the art was like a few seconds, 3 seconds. It can also measure 3D electric fields for the first time. We got that third axis by building a special axial boom, which if you're ever over at the last SBSC building, you can see hanging up, one of the flight spares. And it's the first instrument ever to have error bars on the electric field data, which is kind of wild. With particle instruments, you can do that typically by count rates. You can say, well, I have some Poisson counting statistics or something, and I can use that to give roughly an error bar, but never that's been done with field instruments until this spacecraft. So it did a lot of firsts, does a lot of kinetic physics, but it requires 100 separate instruments to do this, which is just wild. Okay, there's a list of them, great. So things to remember, here I am at the end. Yeah, I'm at the end. The primary goal of an in-situ measurement is to take a field or a particle and turn it into a voltage. Once you accomplish that, you're more than halfway there. Every spacecraft instrument is unique. Literally every single one. Even if the instrument itself is the same from mission to mission, the spacecraft is different. Your environment is different. And so it's hard to say these are artisan instruments. These are pieces of art that are used to measure things. There will only ever be one made of most of these things. And you only build something like 2 to 3 per decade. These are rare, special things that all behave differently. And once you build one of these things, you can never change it, right? Say you've launched it on Voyager out of the solar system, you are never talking to that thing again. You can communicate with it, but you can't manipulate it. You can't fix it. Whatever you build is what you built. And it's built, of course, very well, right? These things are built to survive decades in space under incredible thermal conditions, radiation exposure, and wild vibration during launch. These are incredibly low power instruments. Does anybody know how much power your laptop takes? Those bricks that you plug in? Anybody ever read it? It says on there. 90 watts, right? So 90, 100 watts, something like that. You know how much power a spacecraft instrument takes to operate? An in-situ instrument, a really good one, will take somewhere about 10 watts. That's incredible. You highly compress the data, right? You have this very poor connection to your spacecraft. You have this 1/r² kind of issue where your spacecraft is trying to broadcast back to Earth, which is very far away. You lose information very fast, or at least power. And so you compress the ever-living crap out of your data. And when you do that, you introduce these approximations and errors as you try to decompress it. So there's that problem. And your spacecraft always gets in the way of an in-situ measurement. Now, people who do photons sometimes care about the spacecraft for things like glint or thermal expansion. But in-situ measurements, you're always worried about the spacecraft. This is like, you're trying to measure an environment that you are disturbing. Like trying to measure the temperature of the ocean by putting the thermometer behind your boat, right? You're going to get the wake and everything else messing with it. So these are the things you worry about when you try to do meta-analyses like using machine learning techniques. And everything matters, where you put it, how the spacecraft accommodated you, what booms you put it on, what the operation plans are, all those things matter. Now, this overview I've given you is really just barely scratching the surface, right? This is just a broad overview, a rough idea of how these kind of instruments work. There's a lot more to it. Yeah. And every one of these sensors, everything you try to measure is done differently. They're all unique. And then finally, the final point I want to make is that a lot happens to your data. Trust your data, but verify any trends you see, verify where it came from, try to understand what the patterns are. Don't just assume that the pattern is natural. Because so much happens to the data along the way. So as scientists, of course, our job is to be inherently skeptical, to not believe everything we see, to look for faces in the clouds, but not believe their faces all the time. Trust but verify. And then finally, whenever you come across a data pipeline or detector pipeline development, try to understand how much went into that and how many people are involved in making that happen. It's a huge effort to get from that particle hitting your sensor into that science data product that you can then use to understand your environment. So I give you this. This is a collection of papers in 2016. It's a collection that comes along once every 10 or 20 years. I think there was a 20-year gap between this one and the prior one. But it is measurement techniques in solar and space physics. And it kind of lays out, it's a bunch of papers that walk through the measurement techniques that are used to measure all these in-situ quantities and even a bunch of the remote sensing quantities that you'll hear about after. So this is a good place to start. Of course, it's 10 years old at this point, so technologies have changed, but it gives you the basic understanding of how these measurements are made. So presumably these slides will go around and you'll get this kind of stuff. Okay, questions, comments? I'm at the end. Oh.
I have a question to start with. I want to follow up on Louis' question.
Yeah.
If I'm a student and I'm looking at data and there's something funny in it and I don't understand, who should I talk to?
The instrument team. Always go to the instrument team.
And they're nice people.
They want to help you. Yes, absolutely. They want to help you.
Data.
And these instruments, again, are so rare and so unique. You really need to go to the people who either work with the data all the time or the people who built the thing. And they'll be able to tell you, oh, yeah, that's a whatever. That's the power supply making a hiccup every 30 seconds. Or that's when the spacecraft happens to be looking in a particular direction. This odd thing happens. Um, so yeah, whenever you have a question or something seems unusual, you find a weird pattern that doesn't make sense, take it to the instrument team, take it to someone who's very familiar with the data. Okay, questions? I guess we got a box.
Yeah, so okay, it's working. Uh, can you go back to the magnetograms, the first one? I forgot the name.
The magnetometers?
Yeah, sorry.
Yeah, the flux gate?
So yeah, so can you please explain how this is able to get the direction as well?
Yeah, so what you end up doing is you cover it in this, there's two windings. One is the drive winding. That's the one that's forcing the magnetic domains back and forth. And then around that, you put a sense winding. That sense winding senses only magnetic fields in a particular direction, right? Because that's what's going to induce a voltage in that coil. So by orienting the sense winding, that's what's going to give you the vector components. Because it's telling you sort of how the natural magnetic field is perturbing your domain flipping, but only in one direction. So often what you'll do is you'll have one sense winding like that. You'll take another one and put it on its side on the same core. So one of the cores will have two dimensions, and then you'll need a second core to get the third dimension. And you can see that, I think, in this picture. Yeah, here. So one of these cores is on its side. There's a torus under there. And what you're seeing in the red or copper color is the sense winding. So there's two sense windings on this one, and then you have another core with a third sense winding there to get the third dimension.
Okay.
Now, one of the troubles with this is physically mounting them. How do you make them exactly 90 degrees? That is a non-trivial problem. And then how do you verify that they're actually at 90 degrees? So another problem with flux gate magnetometers is trying to understand the error in the pointing, because that coil may be ever so slightly misaligned, half a degree. But if you're off by half a degree and you're trying to measure 1 nanotesla out of 100,000 nanotesla, like half a degree becomes huge.
Okay. And then like the range of measurement of the flux gate, is it like does it measure specific range, usually high, low, like?
It really depends on how you set the gain. So flux gate magnetometers can be gained to measure very different ranges. They're used on Earth, again, for things like submarine detection. Sometimes even used for, versions of them can be used for like the things that scan you as you walk out of a store, make sure you're not stealing something. There are things like that that can be used. So you can scale them to operate basically up to 100,000 or more nanotesla. So more or less like 2 to 3 times Earth's field. You can make them much stronger as well for higher fields, or you can scale them back to pretty low fields. But once you get down below about 0.1, so 10 picotesla, they get really hard. It can be done, but the signal to noise is very poor.
Thank you.
So how do you add error bars to a electric field measurement?
Yeah, so one of the things on MMS is it also has a thing called the electron drift instrument. So it's an electron gun that fires pulses of electrons that then move out through the plasma, undergo an orbit, and then reconnect sometimes with the spacecraft, and they get measured. When that happens, you get a sort of measurement of the electric field, because you can measure both. You know the magnetic field, you know the particle trajectory, and which energies make it back to the spacecraft, and then you can infer the electric field. So a lot of times what they'll use is the 3-dimensional electric field measurement from the antennas, and they'll calibrate it against that signal. And so that's a way you can get the DC measurement calibrated really well. For AC measurements, it's a lot harder. There's no like wonderful way to do that because you don't have like a standard candle to measure against. So often with AC measurements, we're not so much worried about the amplitude, we're more worried about the frequencies. And then the amplitudes we assume are probably uncertain to a few percent.
So I have two questions about the electrostatic analyzer.
Sure.
I mean, the first one will be because uh, I think that when you want to tell the composition of the ions, there's currently like two techniques. One of them used in a time of flight system, another one is to use the magnetic field, and you can tell the charge mass ratio by taking a radius. But I think from the papers I've read, I think most people are using the time of flight system instead of magnetic field. Why is the reason for that?
So there's a couple of reasons. One, when you use one of those magnetic systems to separate out the charge to mass stuff, you have a finite look direction. So you're basically, again, looking down a little cardboard tube, and then you have to move that cardboard tube around in space. Whereas an electrostatic analyzer, you get a torus, and then you can move that torus around in space. So your field of view is much, much better with one of these things. So you can get faster measurements because you're measuring more of the sky at once. The other reason not to use a magnetic spectrometer is because of the magnetic fields. You're creating on purpose a giant magnetic field right next to your magnetometer that you're trying to use to measure the environment. So if you care about the magnetic field at all, you hate that instrument. On the one hand, it gives you beautiful energy resolution, and there's no better way to do that, right? But it disturbs everything else. And so you have to make these trades. What do you really care about? How long of a boom can you afford? That kind of thing. So the problem with in situ measurements is that you don't focus on one instrument typically. It's how that instrument interacts with the spacecraft, interacts with the environment, interacts with every other instrument. So the decisions that get made are holistic decisions, not focused.
Okay, my second question still about that is, so sometimes when you want to measure different species of ions, right, there will still be some crosstalk problems. For instance, when you look at the ion spectrogram, even if you are trying to see the protons, but you're still seeing some signatures of heavy ion spectrogram there. I think that's the crosstalk problem. So when you really send a spacecraft into space, how do you know how you're going to fix that problem from the ground?
You plan as best you can, right? You take whatever previous mission has been there or whatever environment is similar, and you try to either test or design for that expected environment. But maybe you're thinking of something like Juno Jade, for example, which has issues with, like you said, separating species. They did the best they could, right, with the knowledge that they had before launch and the design capabilities at the time. This is why we often iterate missions, right? So there was IBEX, right, which went to go measure interstellar neutrals. Well, now there's IMAP because they learned a lot from IBEX about what was limiting the measurement. And they said, okay, now that we've limited, or we know what the problems are and we know what we're trying to get to scientifically, we can refine the instrument. So often what you'll do is you'll send your very first mission of exploration to a new location with as general of an instrument as possible. And then you'll send a follow-up mission that has the more specific stuff. That does, now that we know what the environment is or what ions to expect, we can tune our instrument to get rid of those kind of crosstalk issues. So it's often done with iterative missions. I don't know how much time I have. I feel like I'm way over, but it's cool. Oh, hell. Okay, great.
So to follow up on the
Okay.
previous question, do the instruments influence each other? Like for MMS, you have a lot of instruments there. So do you have to switch them off at some point, like for certain measurements?
They all influence each other. Every instrument influences either the plasma or the other instruments, always. For in situ measurements, that's particularly strong kind of issues. So on MMS, yeah. So for example, when we're using the electron instrument, right, the electron gun instrument that fires them off and then looks for the return, that disturbs the ambient electron measurement, right? When we're trying to use the electric field instruments, one subtle detail of an electric field instrument at DC is that you have to current bias it. So I have to drive a current on those probes to kind of get it to the plasma potential. When I do that, I change the potential of the probes, which changes the potential of the spacecraft, which makes it so different particles can enter the electrostatic analyzer. When the spacecraft turns in a certain direction, like on MAVEN. So MAVEN is a mission to Mars to look at ionospheric outflow. It has big old solar panels, right, because it's operating at Mars. When those solar panels are facing toward the sun, you get totally different electrostatic and magnetic responses of the spacecraft than when they're like 90 degrees to the sun. Everything disturbs everything all the time. And even if it's not physically disturbing the environment, the systems inside disturb. For example, on Solar Probe, we get this beautiful signal in all our electric field measurements right at 1.2 kilohertz. That's the Faraday cup. This darn Faraday cup, where'd it go? This guy has a modulation at 1.2 kilohertz. They change the potentials on the grid at that voltage, and I can see it clear as day in every electric field measurement. The power supplies, the data rates, some instruments do processing. So the electric field instrument, for example, gobbles up a bunch of data and then takes that chunk of data and processes it maybe into a spectrum, something else. While it's doing the FFTs required for that spectrum, the processor needs extra power and it operates at certain frequencies. That radiates into the spacecraft and all the other instruments pick it up. So every instrument is going at a different cadence, a different rate, doing a different thing, and they all disturb each other. Yeah.
Do you have observing plans for that? Like where you know, okay, we want to measure like a certain thing, so we switch off this instrument, for example?
You typically don't switch them off in the sense that when you want to measure in situ plasma, you want everything, right? So say you're trying to measure Ohm's law, which is kind of what MMS was really designed to do. And you think about all the terms that exist in Ohm's law, right? I need the densities, I need the temperatures, I need the velocities, I need the, because I'm trying to get pressures, right? I need to know the magnetic fields, I need to know the electric fields, I need everything at once. So the typical approach is to leave everything on all the time and then just try to figure out which of the signals are real and which are created by the observation. And then to either filter them, remove them, or ignore them. Depends. So this is another thing that's different between every single instrument and every single mission. This stage, how much calibration is applied. And there are different philosophies to this. Some philosophies say you should apply as little calibration as possible because you want the data as raw as possible so that you can find anything that's in it. But if you only hand a scientist raw data, there's no density or temperature or anything in that, right? So if I go to, for example, on Solar Probe and I try to look at electrons, what do I get? I get a number of counts in a particular anode in a particular look direction. How the hell am I going to get a temperature out of that, right? Like what I really need is the instrument team to go through and draw the full distribution function and fit it and try to get an idea what the temperature is and just give me a temperature. But they don't do that because their philosophy is if I do that, I'm introducing errors. I'm introducing uncertainties and approximations that the researcher no longer knows about because they're hidden under that layer of processing. Other teams say, well, we want to make the data as usable as possible. So we're just going to say that all these approximations and errors exist and just give you the densities. Which is better? I don't know, right? One requires more specialized processing to use, but hides some of the, or keeps all the errors and bumps and wiggles and stuff right where you can see them. The other one kind of hides them, but makes it more usable. I don't know. So every instrument team has a different approach to this, even on the same spacecraft, even in the same instrument, right? So this thing, if I go look at the electrostatic analyzer, see how there's two ends? That end is the ion instrument, that end's the electron instrument. I can go to Solar Probe Data Archive and I can get velocity and density from the ion side of this instrument. I cannot get it from the electron side. In the same team, they disagreed on what to do philosophically with the data. So that's something that has not been well standardized and not been well organized, I suppose, across missions or even instruments or within the same instrument. Tricky stuff.
I have a question that I've heard that measuring electric field is more difficult and less accurate than measuring magnetic field. But if you are measuring voltage anyway, why is measuring electric field is more difficult? Is it because like it is easily get influenced by the spacecraft itself and other instrument or something like that?
The real problem is this delta X, right? So we can measure the voltage very well. But what is the distance between the 2 points where you're measuring the voltage? With an double probe instrument, that's a little bit straightforward. Where do I have that graphic? Here. With a double probe instrument, I might just say it's from the red dot to the red dot. And I might say that's my distance. Yeah. That's not exactly true. So what happens is that boom that you're using, that mechanical structure that you're using to separate the probe from the spacecraft, also interacts with the plasma. It also has a plasma sheath and a potential. So when you're trying to measure the potential, that delta X is very uncertain because it can be anywhere between the probe and the spacecraft.
Okay.
And every time the density and the temperature of the plasma changes, the electrostatic center changes. So literally every wiggle in the plasma moves your baseline measurement, which makes it really hard to figure out what that is. So sometimes we can calibrate it with natural phenomena. We can use things like Whistler waves. If you have a Whistler wave and you can apply the cold plasma approximation and you can measure the magnetic field, you can back out the electric field very precisely. And you can use that to calibrate. That's what we did on Van Allen probes, for example.
Okay, thanks.
Yeah.
I have two questions. The first one is if I'm having my data in the form of velocity distribution function, is that considered calibrated data or raw data?
Again, it depends on the instrument team.
Okay.
So there are calibrations that go into even creating the distribution function. And then how do you get from the distribution function to the fluid moments is typically some fitting procedure or approximation procedure. You know, but that fitting and approximation, there could be many, many procedures that give you slightly different answers.
Even for the distribution function, not for
yeah.
the moments?
Yeah, absolutely.
Okay. The second question is, if we have the cadence of the instrument is either smaller or larger than some time scales of the phenomena that happens in the plasma. So it might not capture all what I need. So how do I know that I'm missing something?
So often what happens, for example, with a particle instrument, let's say you're trying to measure a velocity distribution function. The one I'm most familiar with is, let's say you have a beam plasma instability. So you have a background plasma and you've introduced a stream of very fast particles. Those fast particles then grow plasma waves, and as they do so, they change the energy of those particles and they flatten the distribution. That process usually happens on like kilohertz time scales, 1 over 100,000 quantity seconds. So it's very fast. But your particle measurement might be 30 seconds. So what ends up happening is that you are measuring the moment where that instability happened, but you're also measuring the other 30 seconds of data. So typically what happens is things get smeared or averaged or smoothed. And so when your cadence doesn't match when your cadence is much slower than the phenomena you're trying to get, you end up measuring a smoothed version of it, which typically reduces amplitudes, smears out distribution functions and moments, and just generally makes things seem, more smeared than they actually are.
So I look to the evidence of the event, not the event itself.
Often. So for plasma waves, that's usually what we do. And one of the reasons to measure plasma waves at all, especially high frequency waves, they may not be doing much in terms of exchanging energy in the plasma. They may not be accelerating much, but they are indicators of kinetic processes that you cannot otherwise measure. So often what we'll do is we'll use the higher cadence measurements on some instruments to tell us what must be happening on the lower cadence instruments. You infer it, typically. And that's where things like simulation become very, very valuable, because you say, okay, I need to have these particular conditions in this particular environment in order to create this effect. We can measure the effect, but maybe not the cause.
Thank you.
Yes, I will hang around through lunch.
Okay,
So.
since we have a queue, we 5 minutes of.
All yours.